Well, I'm very happy to be back in Valencia. And I'm charged with the paella, which is great. Okay, so what I'm going to talk about today is like a read update on my research topic and AI for scientific discovery. But before going into that, I think we need to review what are the kind of status in the AI, particularly in the AI in the physical real world. Because like a scientific discovery, we're talking about the real world. We need to understand what's going on out there. So what is we're trying to achieve in the scientific discovery is we want to understand and to be able to control and a very large-scale complex adaptive symbiotic systems. Either it is like a cell or a whole human body or environmental or probably like a financial or urban architecture. You know, it spans from the biological, all kind of system we are facing with. Like this is something we want to accomplish, not just to understand, but to be able to control it. Because when we want to cure disease, like we need to be able to control the state of the body, which is like a malfunctioning, or you want to actually intervene to the urban environment to be able to fix the problem in the city. And almost 10 years ago, I proposed a Nobel Turing Challenge. That is a challenge by year 2050 to be able to build like a highly autonomous AI agent to make like a scientific discovery highly autonomously and continuously deliver the discovery at the level of that might worth the Nobel Prize or probably beyond. So this is one of the grand challenge I proposed 10 years ago. Of course, you know the other grand challenge is RoboCup. By 2050 to create a fully autonomous human robot team to beat World Cup champions. And RoboCup is going on as we speak now in Incheon, Korea right now. And then that's robotics version. Of course, like a human World Cup is going on as we speak now. And unfortunately, Japan is kicked out already. But anyway, so I can concentrate on the research now. The Nobel Turing Challenge is a challenge and the questions. Challenge is, can we build a machine like that? Can we build a machine to be able to make a major discovery, the worthy of Nobel Prize? And the question is, if we can build a machine, does the machine look like a human scientist, or are we does it going to show the very different kind of intelligence? And therefore, whether it will pass a Turing test will show something very different. And my bet is like, I think like a machine is going to be very different from human. But anyway, we'll have to see. Now, if you look at the history of the AI has been a history of the grand challenge, from the computer chess to shogi or Go. And well, this kind of a game is like a complete information game and then a turn taking. And this is like an amount of like computing required to solve the problem and then all the space complexity. And even if you got like a bigger problem than the Go, I think we know how to solve it. It's just a matter of like how to get the data sampling, and then we got the how to get the computing power ready to solve the problem. But the challenge is like if you got it the real world, like autonomous vehicle or suckers or like scientific discovery, that we have to face the messy reality of the physical real world, and that's actually challenging. Now, at the same time, there's a lot of interesting stuff going on last decades, starting from the beginning of the deep learning. For example, take like a very few small example, like this is a deep mind, and then the EPFL has managed to get the high precision plasma control in the fusion reactor on this, that's in the EPFL campus. And this is a Nobel Prize winning work on the predicting 3D structure of the protein from the primary sequence. And this is really, groundbreaking. As the interesting one is this Kikero, which is like a meta AI. It is, superhuman, diplomacy player. Diplomacy, as you know, is like a diplomacy game in Europe. And then, the gamer need to persuade that you better be on your friend. So that means like a Kikero, this AI agent is much more convincing than any other human players. Okay, so. Well, this underlines some of the discussion we have, like an agent can be more persuasive than the human peers. And that's something going on right now. And then now I'd like to show you some of the research we did at the Sony AI. And then there are some of the recent papers from the Gran Turismo, and we have like a very fair and then unbiased like a data set for the data set for like face recognition, like a human posture recognition. Also, the one we published like a couple months ago is like a superhuman athlete robotics for the table tennis. Let's start from this Gran Turismo. I want to focus on the Gran Turismo and the table tennis in the very beginning of my talk. We have like Gran Turismo is like a PlayStation game, and it's extremely realistic driving simulations. So to be able to outperform the best human player in the world could actually potentially be the best also in the physical real world. Although this is a game, but Gran Turismo is extremely good driving simulator. And then what happened is like we trained the AI. This is basically deep reinforcement running, and then all the scenario-based training to be able to outperform the best human driver in Gran Turismo game. And of course, like there's like a esports championship, and then we got the one of the 5 of the top athletes, and then to be able to play against the AI agents. So this is a car in the white, that's driven by the human being. And then with the color, like a green or a purple, and that's AI agent. So now you can see like this onboard camera, that's, we call it Sophie bed. This is like a green one, it's like an AI agent. And to be able to, overtake and then win this championship game. Now, you can see like Sophie's, this AI agent making tactical decision right now. They're actually going after this car, and then whether this car will overtake like a human driving car on the corner. Now it's going inside here. So they can not just like driving faster, they have to make a decision so when to overtake, when not to overtake, and they make like all the tactical decisions. Now, once AI cars overtake a human driver cars, they are very fast actually. For per lap, I think it usually like 2 seconds faster than the best human drivers. And after we accomplish this superhuman capabilities, we put this AI agent actually online to be able to be played by the gamers around the world. Obviously, no one beat the AI agent. And that doesn't make a very good game because people come to play the game and get humiliated. So we decided to do is to put more capability, additional capability for the agent to be able to adapt to the gamer's capability, so the gamer can enjoy a very realistic game, against the human players. Now, if we are playing, PlayStation 5, GT Gran Turismo, most of the non-human car is based on this AI agent. So this is like one of the most widely used agentic AI in a gaming world, probably even beyond the gaming world. Now, if you look at this like a trajectory of the log, we can see like why humans know much against like AI agents. So if you look at this steering and then also throttle and brake, and the blue one or the black one is a human driving log, and then the orange one is the AI agent. So AI agent can actually adjust like a throttle and then steering in the millisecond order, and human cannot do that. So like AI can completely outperform the human capability in the precision and speed. And obviously, once you tune that well, it can't really, human cannot really match. We took it further, not just like a conventional racing circuit, to do the drifting game. So drifting is that you have to control the sliding mode, right? It's very difficult. If human players do the drifting in the circuit, you have to be lucky to be able to come out the corner in in an intended way. So this is, although this is simulation, the very realistic, this is like an AI agent controlling how to do the drifting and plan the trajectory and to be able to control the car to be able to go, as it planned a priori. So it's really difficult, you can see, and you don't want to try yourself. I mean, that's going to be really risky. But like an AI agent can really reliably repeat this drifting mode. Okay. So this is like a state of the art in controlling the vehicle. Now, then people ask questions like, can you actually do it in a real physical car? That's very expensive, actually. It's like we decide to go for a little bit more affordable challenge to be able to beat best human athlete in a real sports. And we pick up table tennis. And the reason why we take table tennis, we can do it in-house. inside, not outside the field. So we can do it outside. It's just a matter of the budget, okay? We got a very realistic, physical realistic constraint in a different sense. But we decided to pick up table tennis. And also, you want to be able to compete against the best player in the world. So we decided to do this in Japan and in Zurich. And the Japanese table tennis player is one of the best. We are competing against China. Sometimes we beat Chinese players. Sometimes we lost. So China is slightly in the edge, but a Japanese player is in the top tier. So therefore, we will be able to play against the best human athlete if we do it in Japan. So we decided to go for this, and then we created an entire robotic system and AI to be able to beat against play against the best human player. Okay. So there are a few. I think it's the videos should be coming. Yeah. So we got a setup here in Tokyo and Zurich, and that is a kind of robot. Unfortunately, it's not humanoid yet, but now she's one of the top players. This is this elite player. She's actually probably one of the top 10 in the Japanese table tennis league. So last month, this system actually beat the two-time silver medalist Olympic Games, Miyu Hirano, and then with 11-6, 11-5, and the second game was 11-6 and 11-4. So this system actually beats potentially the top-tier Olympic medalist scale athlete in a big margin, and that is the current state. Now, let me show you what's behind this. Okay. So this is actually a very slow-moving one. Okay, now you have all the trajectory. That's a prediction trajectory. You look at this a prediction trajectory going on. Now it's touch the net. So all the prediction is not touch the net, but the reality it touch the net. So you change the course. You capture that change right away and do the simulation. What is the new course, and then readjust it the robot motions in a sub-millisecond. And otherwise, you can't really go against this kind of player, right? So that is something we did. So there have to be always real-time prediction, vision recognitions, and then tracing of the ball, and then simulations, so the trajectory could be, and then always checking with the reality and trajectory. And if that diverged, then recalibrate the entire simulation and then make different tactical decisions, and then move the robot. Everything have to go in a millisecond order. Otherwise, you cannot compete against it. And then we had a very special vision system created by the Sony Semiconductor Solution, which is events-based sensor. It's okay, this is the image that we got. So, you're tracking the ball, and you can really see the rotations. It says this is 200 radius per second, and the speed, 4 meters per second, and you can see the axis, and then you can see the trajectory. Yeah? So you can, on the real time, you can predict, and then how it bounces back, and then you can see the aerodynamics and everything. So you need this kind of a sensor to be able to compete against the best human player in a table tennis. So this is events-based sensor. It's not a frame ratio, but basically this sensor is equivalent to 1 kilohertz frame ratio or above. So extremely fast sensor to be able to detect what's going on. And then, okay, so those are the things we did, and then then the whole thing have to go in a millisecond order, so that the engineering is really key. It's reason why we accomplish this is not just AI. We have that, really deep engineering capability to be able to, have a sensor, very special sensor. And then if you try to move the camera, you can't really track that because the camera is heavy. So what we have to do is a multiple camera. And I get the stereo to actually be able to, a multiple stereo to be able to capture dips, and then we put the mirror in front of the camera to be able to move very quickly. So we have to have our engineer to have the extremely precise and fast-moving mirror gimbals to be able to track the ball and keep it tracing with that speed. And then all the internet connection has to be on very low latency. And also all the physical realistic simulation as well. And the robot, if you got the robot arm, if your arm is heavy, you can't really cope with the change. If you have put a net and you got a trajectory change, you can't really cope with that. So we actually decided to redesign entire robotics arm with the carbon composite and a very lightweight, but still the very strong arm. And then we did it completely on the 3D printers and then the autoclaving. And that kind of end-to-end engineering has been really the key. So we all talk about physical AI now and talking about focusing on AI and computing capability, how much of the GPU you have. But at the end of the day, you have to have a good engineering integration capability to be able to do high-quality physical AI. I think this is a down-to-earth reality, and how, if we are going to the physical AI. Now, scientific discovery go further beyond. We talk about this Gran Turismo, we talk about table tennis. That's a sport, so it's a defined search space. It's a physical realistic, very fast-moving, but it's really defined. Now, the scientific discovery is completely open-ended. So it's not defined at all. And to me, scientific discovery today is like a pre-industrial era. If you're in biology, you can do a genome sequencer, like mass spec, you get a lot of data. But at the same time, after you get the data, we have to really think what this data means, and we have to really do the analysis by ourselves and everything, And that part is not really changing. And I want to change that. Now, this is one of my early study in biology about aging study. So I started in 1994, and we got 4 years to come up with theory and experimental verification of the theory or the very first cut, and we published a paper in 1998. And then we continued to experiment with a mouse model and everything, and then some of the hypotheses has been verified now in the 2000, and then we got the first clinical trial in 2016, so that's 10 years ago, and still going. And this is a time scale in biology. It's pretty long, actually. So can we actually change this? Can we actually make it shorter? Instead of taking 2 decades, 3 decades, can we actually change the entire process to be done in 2 years or 3 years or maybe 5 years? So which part we can speed up? We can speed up in the hypothesis generation. We can make hypothesis much more accurate. Or we can have experiment that move faster. So every aspect of the scientific challenge, particularly in biomedical science or material science, they are bottlenecks, and I want to solve that. Now, at the same time, the reality is we may not be good in science. In biomedical fields, over 2 million papers get published every year. Okay, if you are in a area like oncology or neuroscience, immunology, hundreds of papers per day. You can't read it. And we think we know something, but we are actually navigating in darkness. We don't, we are actually looking at a very small fraction of what has been discovered, what's been discovered every day, and that's how we operate. So that's actually we are trying to discover based on knowledge we know, but it's a fraction of knowledge. And that's it's a human cognitive capability, actually. At the same time, this system is awfully complicated. This is a diagram of the yeast cell cycle. This is a very small yeast cell, which actually used for the wine brewery. And it's a very small fraction of the cellular functions. We actually did how the molecules interact with each other. And we read 1,500 papers and go into the details and create a very detailed and very accurate map. But we cannot continue this. Human continue to work on this. It's not possible. It's psychological not possible. It's a really psychological burden, and there's no career opportunity after doing this. What kind of job you can get is very minimum. It's also funding-wise very difficult to get funding. But you have to do this. You have to really get a whole picture of what's going on. And previously we didn't have any ways to actually automate this. This has been a highly labor-intensive process creating a molecular interaction database. There's EcoPsych and all kind of database there, but it was really done by human. And now, with a large language model doing properly, we can automate most of the process. Not entirely. We need to double check, and then there are errors associated, but we should be able to automate pretty much a quite substantial part of this process now. Now, the other thing which is interesting, there are 40,000 human genes in a human genome, coding and non-coding altogether. And I picked hundreds of them randomly, and I counted the number of papers published. And this is a statistics, and this is very consistent with much larger study. So 96.8% publication on top 10 genes. Okay, this part of the gene, there's no paper. Okay, so that guy actually a few years back did a very comprehensive study in 40,000 genes, and surprisingly, 60,000 of them have no paper. Another 7,000 has only one paper. They get the same distributions. 96% of the paper is on top 10% of the genes. And why? Because scientists want to be successful. Science wants to be able to contribute. Therefore, scientists focus on the gene that is considered to be important or probably likely to be important, rather than randomly pick the genes on the tail end of the distribution. Now the question is, what are we going to do with that? So if you have like a postdoc and or students saying randomly pick those 5 of genes, and then okay, this is your thesis, and then if you are lucky, you're going to be the star. Otherwise, I'm sorry for that. Yeah, of course, your student will shout like, "Oh, what happens in my life?" You know. So it's very difficult for the human to be able to randomly pick those genes, and to be able to bet on the carrier. You know, of course not. But the question is, are those genes important or not? And this is one example of the genes, which is TREM2 genes, which is considered to be extremely important neuroinflammation, neurodegenerative disease. 2000, there's no paper. And there's a small number of paper published, like, first 10 years has only like a 4 or 5 paper per year. All of a sudden, it turns out this is going to be extremely important neuroinflammation, neurodegenerative disease. Now, every year, over 20,000 papers are published. Now, there must be many other genes like this we just haven't discovered. But at the same time, even if you get, start working on one of those very important genes, which is completely ignored right now, but you probably have to endure this 10 years. There's a very small attention that's been paid, and there's some key moment to shed light on important specific topics. So how am I going to do with this? It's very difficult for the human. Also limited career, opportunity. You can't really be in a dormant for a decade if you want to be successful in the scientific career. You want to be a success much earlier in stage, but this is the reality. So the solutions is we're going to do it in AI and robotics. Now, and this kind of distribution is not just in the biology, but if you look at all the real world, if you got the frequency of event or probably importance event and the rank distributions, in a controlled environment, like factories, this tail is cartel, so you can control. But in the real world, this tail is long. And even if the long tail, if accumulation of the tail side go up to 30 to 40%, or sometimes 60% of the entire event. So you cannot ignore a tail, but the same tail is a tail. Event is very rare. So you're gonna actually hit something very important in that tail end is slip. But a tail is extremely long, and how you do with the tail is really the issue in AI. Now, if you look at this is a training curve in GT Sophie AlphaGo. GT Sophie, 2,000 cycle is enough to actually beat most of the player. But to beat a world championship level, we need a 10,000 cycle. So this is 80% of the cycle computing time was spent to improve last 5% or last 3%. To beat most of the people, to beat the human champion. That's actually a 3 to 5% improvement, but then you need 5 times more computing power. The same in AlphaGo. To be able to beat most of the human players is 4 days, but to be able to beat a world champion class is 40 days. And this tail side is where the resources need to be spent, and that's really the differentiator to be a good enough AI to be the super performance AI. And this is the fundamental issue. It's not just a design, it's a fundamental law of this nature of the complex system because they are tail side. You gotta take care of the tail, otherwise performance don't increase. But to get a tail, and you have to spend computing power. And you have to keep collecting the data, and this is the fundamental. Now, go back to the science, and then science, same thing. It's we're going to have the tail side of the science, which is actually grossly ignored, but you have to be lucky to be able to hit the tail. And then high-precision simulation, AI, and automated experiments are things that you need to be able to speed up entire scientific discovery process. And then I look at some of the Nobel quality discovery. In case this is an iPS cell by Shinya Yamanaka. So it's very interesting. He initially studied iPS is this is a cell taking the body, and you got the regenerative medicine, stem cell, creating a stem cell and form the somatic cell, and to be able to differentiate any of the cell you want. Okay, this is like a groundbreaking discovery, won a Nobel Prize in I don't know which 2012. Okay. Initially interesting, he has been working not on the regenerative medicine or stem cell. He has worked in the cholesterol. He actually studied how to reduce the cholesterol in Grad School in San Francisco, and then found that ApoBec1 is like a thing that you want to edit, and then you have like a messenger RNA editing, and then after like overexpression ApoBec1, and he see the mouse has like a reduced cholesterol, very successful. At the same time, every mouse who got the overexpression ApoBec1 has a liver cancer. And then he found out there must be some collateral target which is undesired, and he found out NAT1 is actually the collateral target, and he found out NAT1 is not just like a causing cancer, but like a reason for causing cancer is actually change the cell fate dramatically. So like, he came up with the idea there must be other genes, not just NAT1, to be able to control the fate of the cell, which could to be able to reprogram the cell fate. And then he actually decided to search for the other genes of the similar property, where he says the ECAT, ESO-associated transcript, and he found 24 genes can be like a candidate, and then put everything on a cell, and then he managed to reprogram the cell. This is the big discovery. And then he further optimized the liver experiment to identify what are the minimum genes that require to reprogram the cell, and come to the 4 genes, which is now known as the Yamanaka factors. So this is more the exploration space, which is like a really connecting a dot in the very far apart, starting with the cholesterol, nothing to do with the regenerative medicine of stem cell, but actually he found out, completely by accident, found out there's something related to the stem cell, and then this is like optimization process. So like optimization, I think like we can reasonably understand that robotics and AI could be good at it. So like how actually go to the exploration space is very challenging, which should be very interesting. Now, CRISPR-Cas9, Jennifer Dowden and Maria Sharpanti, and then they've been working, there's a long history of like how the, the microbial can defend from the virus invasions. And there's like some precursor research by like Ishino, and then, there's no one looked at this for 18 years. It was completely dormant. And then in 2005, there's something interesting happening, and then there's people start paying attention to this, and then found out this is going to be the gene editing capability. And then after that, identify what is the most efficient bioengineering to be able to cut in precisions and to be able to be efficient. So this is like optimization process. So it's a very, very long exploration stage, and then a very quick and a massive investment on the optimization stage. So it seems like, I wouldn't say like every discovery is like this, but like many discovery seems to have the path of exploration and search and optimization. If this is like specific templates of the major discoveries, maybe we should be able to replicate the process in AI and robotics. It's a long way to go, but at the same time, if we do it in AI and robotics, we should be able to make a larger search space to be able to find the multiple different paths to achieve the final answer. So it's very interesting. Also, with structural biological discovery, basically you won't be able to identify the molecules and their interactions in a very necessary structure on the specific biological process. Either it's a fundamental process or a disease or it's a cure. So we have a specific kind of templates that we want to discover. Now, then we want to automate it. Why we want to automate it? Particularly for the experiment, is we want to be able to have a superhuman precision experiment and a long-tail coverage. This is something we're talking about. It's very difficult for us to randomly pick the research subjects and go for it. You want to be able to pick something you think is going to be successful, right? But our capability to predict what could be the success is very lousy. If you're by 2000, if someone asks you what is your specialty, what you're working on, if you answer artificial intelligence, people think, oh, I'm sorry, I asked that question, right? But now AI is like a king, but if you remember 2000s, if you are old time, I think that was like a winter time in AI, and people didn't want to talk about that at that time. So also very interesting thing will happen is the cost of discovery going to be reduced significantly if we go by AI. I think this is going to be a big change in the future, how we're going to, all the corporate decisions and the scientific decisions as well, but I'm not going to talk about that. Okay, then how to automate it. Now, I think we need to go for like a massive search and verification hypothesis space. That's really the key. And then how we go about this is like we have to have like a cycle of the scientific discovery, and you go everything in a massive scale. So we need to be able to have like a massive knowledge extraction and consolidation from all the data and the publications, accumulated. Some of them noisy, some of them fabricated, but still like our fabrications, our imagination is very limited. Fabrication can be the noise, and then you have probably consistent with what's ground truth slides. But anyway, so like a massive knowledge extraction consolidations, and then a massive hypothesis generations, massive experiments, and a massive verification and falsifications. Okay, so this is already challenging, but at the same time, like how many hypotheses we're going to generate in scientific discovery process? We usually come up with like a 1 or 2, probably 3. We usually don't come up with like a 50 or 100 hypotheses or thousands of hypotheses. But if you want to go for like a specific important area, you want to be able to populate the hypothesis, the entire hypothesis. You want to populate the hypothesis, so that you are not missing anything. So you want to verify every possible hypothesis in a specific problem space. And we cannot do this. We are not good at that. So can we actually create an AI system to be able to populate, entire hypothesis problem space with thousands of hypotheses that worth verifying it? We have to prioritize it because we have a resource limitation. And to be able to experiment and verify all those possible hypotheses. Now, another bottleneck is experiments. Our experimental procedure, biomedical science or material science, is designed to verify small number of hypotheses. 1 hypothesis, 2 hypotheses, maybe 3. But usually our experimental setup is not designed to verify hundreds of hypotheses or thousands of them. So we really have to change the entire scientific process. So what I'm saying is we're going to have a trillion of data, billions of hypotheses, millions of experiments, and thousands of discoveries. And we need this run automatic. And then we have to discover, we have to really interpret what has been discovered, what does that mean to us. So automation science has been done. It has like a reasonable history. For example, like Ross King in the Chalmers right now, when he was in the University of Manchester, he created like Adam and Eve system. This is the very first no human in the loop system. Generated specific hypothesis of each genetics and the experimental system, automated experiment to be able to verify the hypothesis. So this is a very specifically designed one. So like, generates the only one kind of hypothesis and do only one kind of experiment to verify that specific hypothesis. So it's a very special purpose machine, but still, this is one of the very first no human in the loop system. Now, in the Carnegie Mellon University, they have like ambition to have like a cloud lab, like a very large scale, like a gymnasium scale lab populated by the experimental devices. They want us to automate like entire process. Now, right now, when I visited like this 3 years ago, there's no robotics yet, it's a human there, and I got the iPad and they can just doing experiments as instructed. So it's just like Amazon Fulfillment Center, that's small. But like the ambition is populate this lab entirely by robotics, so no human in the loop, and then the people actually, ask the experiments and do it automatic, and then the entire process is going to be automated. So like, CMU is investing a lot in AI for science right now. Now, my project down in the island of Okinawa is like automating the metagenome processing, and that's the very first because I picked that because this is one of the most complex systems regarding human body because the microbiome in our body, like a gut, skin, oral, our environment interaction is millions, a lot, and then it's a long tail. So it's not practical for the human to go after like an entire microbiome where we are related. And also like a human omics is so variable, human variability is massive, and the lifestyle is affected. So one of the research we did is like trying to see like an impact of microbiome on the vaccinations. So this is early days in the corona outbreak, and then we get the Pfizer vaccine, and then we actually took a sample of the blood and then vaccinations and then how the immune developed. And then together with like a gut microbiome as well. And we found that like 1% of populations, even after vaccination, don't develop sufficient immunity. T-cell cross-reactivity is low and the antibodies not developed well. And we found out very specific like a microbiome composition, gut microbiome composition is actually preventing to build up like immunity even after vaccinations. those people are actually healthy individuals, not like an immunocompromised individual. So they think they are okay, but because of a specific gut microbial composition, they have less immunity even after vaccination. So this is very interesting, and this kind of thing has been observed in multiple cases, but this is one of the first studies identified why there are very specific group of people who don't develop immunity even after vaccinations. So the microbiome affecting a lot in immunity and the mental state and everything that we know. And the other thing which I find interesting, this is like this Chinese traditional medicine study which we did. It's all the herbal medicine, the combination of 4 herbs, and it's the Maoto, which is the name of drug, considered to work very efficiently against influenza and then other infectious disease. And we identified 352 chemical compound in egg extract. And then we give it to the mouse and the rat, and I measure the plasma, what's in there. Surprisingly, out of 352, only 22 has been identified in the blood, and then there's many unidentified ones, and there's an endogenous one which is elevated by the stimulation of all the active compound in the herbal medicines. So this applies not just herbal medicine, everything we eat, all the food like we measure by mass and extract and identify those are the ingredients, but what we actually eat and then transformed by the microbiome and put in the bloodstream, that's very different. Basically, we don't know much. And this is extremely interesting, but combination is massive, and we can't really do it by hand. So, and then also, obviously, it's long tail, and I'm not going into that too much detail, but there are all kinds of interesting things going on in this area. And of course, we know why those affect the immunity and other things as well. So, in order to solve the problem at the massive scale, we decided to automate for example, a very first one, the metagenome process. And this is the subway chart is every single step on the metagenome processing experiments, and then identify that, optimize that, and put that into robotics. And this is our system called the MANTA system. And this is like a multiple liquid handler, and also like a robotics arm, 3 arms moving around, and the reconfigure robotic system. But no human in the loop. And if you put one sample on one end, everything taken care, and then put that into a sequencer, and then the result will be directly going into the GPU cluster as well. So this is like a multiple, so this is like one box, and then that generates like a massive data in a very stable quality. And with one of such systems, it's equivalent to 20, 30 lab technicians, and it's run 24/7. So what people say is like a little bit of GPU clusters for the biomedical use and other use, and the GPU cluster are going to be data hungry in the future. So we need very large number of those experimental boxes to feed GPU data. And that's actually what we are building right now. We are building right now the metagenome processing, and then we are working on the metabolome, and then we have like other omics, and then we have a lot of requests from the biologists to work on the IPS, CRISPR-Cas screening, and everything. So our ambition is automating entire biological experiments in the robotics at the precisions, controlled by the AI, and get the data into the GPU cluster in a streamline. That's something we are trying to do. And then, so we're going to create like a world model, so like, not just genomics, metagenome, metabolome, and the virome, and everything. And then that's actually more the experimental side. Then that have to connect to the human side, the human physiology. And then we're actually working with the PhenoAI, which is the company working on the project called the Human Phenotyping Project. It's a very large scale and precision measurement of the human physiology. Working with the hospital to be able to have a very specific measurement of the medical checkup, and also like a metabolome and a microbiome, like a genomics and everything. And then we are working on we already have like 100,000 participants actually, and then targeting over 25 years. So we try to trace down like every individual for 25 years, and every data is privately held with the consent, so we'll be able to have a flexibility to the data use. And that's something we are trying to achieve. And then, so one side, we have automated lab experiment for the sample, and then also like experiments at the cell level, and then a stem cell, and then all that. and or the organoid as well. That's another thing we are working on. And the other end is like a human phenotyping, like almost real human data at the large scale across the boundary. And we want to be able to connect it. So we went to the multi-omics world model. That's something what we're trying to achieve. The data going to be massive, and we have traced over 25 years or more, and distribution worldwide. That means we need to be able to set up a system to be able to have a stable experimental outcome anywhere in the world. So one of the variabilities the human technicians introducing a variability as well, or like a lab setup or the subtle environment. So you want to be able to standardize those conditions. So a very first thing we did is automate experimental process, and metagenome is the very, very first one actually. And then, so what we're trying to achieve is actually the discovery, to be able to streamline data generations and then the modeling and the predictions, the entire scientific process as well. So AI scientists were going to really change the way we do science. And when we talk about this, one of the very typical questions is in science, asking right questions is important. How AI can ask right questions? Well, I want to flip that questions. AI scientists will ask every question, and the important answer may be there to be discussed. So not just like asking one question, which we consider is important, ask every question, and use the capability of the massive, experimental capability, data generation capability, to be able to ask many questions as possible, and the important answer are going to be there. Of course, asking right questions is not going to completely fade away, because even AI has resource limitations. So we have to really get the better questions, but it's asking right questions stems from the reality that the active, period as a scientist, is about 30 years. And you have like a limited lab resource, limited like a budget. So you have to ask the right question to be successful. AI, we're going to change this. You can ask every question, so you're going to have like a scalable experiment system, and with the proper, actual discoveries, we should be able to expect some more investment. At the end of the day, one of the things we need to worry about is when someone gets like a successful AI scientist, we're going to see the monopolization of discovery. And that's actually something people worry about. And that's why every government is pouring the money into the AI for science right now. United States will launch a Genesis mission, which is like a DOE project, Argonne National and Oak Ridge National. And then this is like a big US project. And Japan is pouring money, quite substantial, unprecedented amount of money into the AI for science right now. And the EU is working on that. Singapore has a Singapore project as well. So this is one of the hottest AI area in AI, and then biomedical science, material science, and other science as well. So then the question is, can machine discover? So I have a fortunate to actually be like a Bletchley Park on next Monday. Alan Turing put a question, can machine think? I would like to ask, can machine discover? What does discovery means? I think there are three classes of discovery that we can make. One is the piece of knowledge, this molecule interacts with this, this material has a specific property. Can we discover that? Okay, very specific factual knowledge. That's something like class 1 discovery. Class 2 discovery, maybe like a cell cycle concept, or like a Cooper pair in superconductivity. Something like a very systematic, but like it's local, specific phenomena, to be able to not just like a piece of fact, but actually you change the way you look at things. You can explain why this phenomena exists. And then class 3 is completely new way of looking at things, like a quantum physics, or relativity, or gauge theory. Those are harder for AI at this moment, frankly speaking. But for this one, class 1, I think AI had an advantage. I think we should really go for this is low-hanging fruits. It's not really low. It's tough, but still feasible. We can, create a milestone to be able to achieve this. Now the challenge is out from there. Can we actually get some of the conceptual explanation of the phenomena we don't understand to be able to explain, we got it, we understand things. Okay, this is really challenging. We're more conceptual. And this is like really the game changer. That's a little bit far at this moment. I hope to be able to get this far. But if we go to classify the discoveries, we can go after the class 1, because class 1 is something we are not good at, because we can't really good at all the exhaustive research and then, without risking your career aspirations. Like a class one, a massive class one success might really change the way we do things in, the science. Now, generating, of course, like if you're going to class 2 and class 3, is like it means like a new semantic dimension needs to be discovered. That's actually harder, and we don't know how to do that. Now, but I think like there's like a future in AI for scientific discovery, and then that will really change the way we do science. Probably the way we proceed the civilization, because our civilization is based on scientific discovery and technology to make it into reality, and innovation to put it into society. And if we can really accept the scientific discovery in a massive scale, I think we're going to really see the very different future of our civilizations. And I think like my thesis is like over the next 20 years, things are going to change dramatically, and then I think like AI will going to really see the change affecting our course of the future civilization. Well, thank you very much. I don't know how to do it.
Now, do you have any questions?
Oh, the questions, yes.
Yes.
Questions time.
Yes, that's right. I thought we were going to go into the panel.
Yes.
So my question, you say that the cost per discovery will go down.
Yeah.
It sounds like the cost per discovery actually might go up because of all the robotics and all the handling and everything. But the time to discovery would go down a lot.
For sure, yeah. So I think it's a trade-off. Like initially, you have to have a lot of capex. It's like a more expensive discovery. Like as it can more rationalized, like more commoditized, I think like the cost of discovery eventually go down dramatically. Actually,
one of the things we've seen in the past is discoveries lead to the design of new equipment.
Yeah. Exactly.
One of my favorite things is like the discovery of the restriction enzyme. From the time it was discovered to the time you could buy it as a kit and use it to new discoveries was only a year or so. Right? I mean, just unbelievable recycling. So maybe the capex will continue to go up because you'll decide you want to completely replace all the liquid handlers with something else.
So that we really have to do all the calculations, how things are going to change. Okay.
Hi, I have a simple question. It's, have you ever make a machine compete with another machine? Because earlier you showed us like a machine compete with a girl.
Oh yeah.
But have you ever had like a machine versus machine? And
machine versus machine?
Yes.
In a table tennis?
In a game, yeah.
In a game. Okay, so the Gran Turismo we did, actually. It's like, 2 AI drivers. So we actually initially tried like a self-play, like AlphaGo, like Google did self-play, right? So like in Gran Turismo, we tried a self-play. Didn't work very well because they get too aggressive. They really get aggressive and they get like keep violating all the sportsmanship rules of the game. So like we decided to go for the scenario processing, and then they start having a very peculiar conditions which we don't really happen with against the human players. So like I think like the self-play works in a specific environment where this rule is very rigid, and any of the move is within kind of okay framework. So like in a racing game, like some move is violating like a sportsmanship rule, and then that's kind of more soft rule, and I tend to actually go violating. Also like if you push too hard, if you push harder, you take advantage. So like, there's like a tendency in self-play to get more aggressive because you can take advantage. But in a game of Go, you don't have that. Like you can't really go aggressive. You just put like stones, right? So like a self-play works in that environment, but like a self-play doesn't work if you can really take advantage of aggressiveness, but like it's go beyond. And so it's tend to be too aggressive in a self-play.
So it doesn't work because like two machines have the same logic and they took the same decisions. So
it's not same decision, but like they are drifting to the direction that is actually not, that is actually probably like that actually is prohibited by different kind of rule actually. If they can be completely aggressive, you can just go self-play, and then both player can be extremely aggressive, still okay. Then a self-play may work. But like, it's not just like performance, but also like a sportsmanship that was actually in the game. And then self-play actually keep violating sportsmanship rule.
okay, thank you.
Yeah, we can actually try to incorporate the sportsmanship within the self-play, but then. But like that one is soft rule. It's like harder to actually code, actually.
Thank you so much.
And also table tennis actually is having two robotics like that is too expensive. So.
Hello. Well, first of all, thank you for your speech. It was very interesting, but I have a question. How AI development will change the robotics industry, for example, in medicine?
Well, medicine, I think there's a lot going on, particularly in the pharma industry, try to automate the lab. That's like a big thing in the biomedical pharma company right now. It's something we actually talk about this, like, many of the pharma is extremely interested in finding the new drugs and new medical entities. For example, like Demis Hazabi's isomorphic grab is specifically targeting that direction, so identify to create like a new molecule that will actually work on a specific target, and that part can be more the combinatorial, and then if you got like an AI to be able to identify the possible like a 3D structure, and then the binding pocket, and then you got the computing at the more network level, and it should be able to solve the problem, or probably at least you can make it more efficient. But at the same time, I've been working with the pharma for over like 20 years using AI and simulations, and then the difficulty is like you think like work like those like biological systems like touching completely unexpected places, and unless you have like a data on that, you miss that. And sometimes that have like an effect. Sometimes that's actually cause toxic, some side effect. So like many pharma companies come to me and say, this is the molecule, this is the target. But actually, there are two interesting cases. One is there's the completely unexpected place is touching things which is lethal, and for like they have a serious side effect. So that's really hard. But then that the drug has to be killed. You can't really proceed with that. The other case we find interesting, pharma company think this is a target, this molecule is touching, but actually the real effects come from somewhere else, which pharma company haven't thought about, but actually this molecule is touching it. And that is the real cause of the effect. Those things there, like we are not really good at that. We're actually focusing on this, and we have like preoccupied concept, like this must be touching this, and therefore, and it makes sense because that link is there. But there are other links which is also effective. Other link could be much more stronger, but like I tend to, ignore that. So that kind of thing, if you can compute, we can really solve the problem much faster. At the same time, can we actually create the data, like the entire data of the molecule that the chemical compound might touch? You have to be really ready to be looking to all the tail side of the distributions. So like if you design the AI system, robotic system, to be able to focus on high priority things, you might miss the tail. And then you repeat the same mistake as we do today. So you're focusing on something very specific, which is visible, ignoring like a long tail part, which could be, could be like a turn the table around. And so that's actually, it's like a harder part is the clinical study. Clinical study, you have to do with the humans, and not much, AI cannot speed up. But the key is, can you actually speed up, can you improve the accuracy or like efficacy, and also like eliminate the side effects so that your compound and the cohort selection can be improved. Then although the clinical study costs do not change, the failure rate can be reduced dramatically. It's like many experience with the pharma companies, they have a relatively loose cohort selections. You have to select like what kind of patient you want to enroll in a clinical study very precisely. Otherwise, you enrolled many patients which you know it doesn't work. Then you dilute the efficacy, and it doesn't really reach the clinical endpoint. If you use the AI to be able to identify what kind of individual patient need to be in a clinical study, and therefore drug need to be approved in a specific cohort, then many drugs which failed could have been saved, actually.
Wow, thank you very much.
Well, my question is, how do you think job and opportunities for younger people is going to be in the future, like in the next 20 years?
Your question is how this AI impacts like general people in next 20 years?
Yeah, like for the jobs.
Jobs. Okay. So this is like a very interesting thing. Okay. When I actually attended like a AI Action Summit in Paris last year, the biggest issue in the panel for like all the EU ministers has been like job opportunities. AI going to take up like job opportunities, therefore there will be more unemployment problem. The reality is like in next like 10 years, 5 to 10 years, 95% capability for 9% of people will be, outperformed by AI. I think that will happen. So that the question is, what is the human value, and now where's actually what kind of job we want to have? Like at the same time, AI is expensive. To be able to perform the AI with that level, you have generated a lot of tokens. Then actually like human might continue to have a job opportunity because humans cheaper. So this is really tricky, but biggest problem in AI introduction is the human labor cost is actually tend to be cheaper than the AI computing cost. So that's really, I kind of hate to say it's like a human cheap. It's really, looks like I'm a bad guy. It's like I don't want to say that, but the reality is people talking about it is token economics actually is more expensive than people expected. They rather hire people because AI is getting too expensive.
Because we are doing it all wrong.
Yeah.
It's unacceptable to say that.
Yeah.
AI is more expensive because we are doing it all wrong. Because we are not taking the proper approach. We are building systems. We are pretending that we can create intelligence by the same way that our brains would sync with our eyes. Our eyes are not the way to sync.
Yeah, I think AI functions very differently from the humans.
We are building it wrong, and then we complain that it's too expensive.
Yeah, fine. So if that's actually collected, the AI got to be cheaper. Then the problem is what the humans do. Yeah.
Sorry, that is not the way to go. AI, we are building AI all wrong, making it extremely expensive.
Yeah.
And now we say, we can use people because they are more cheaper. That's really unacceptable.
I know.
In all ways, it's unacceptable.
Yeah.
And we need to start working on AI in the right way, making AI work as it should, and not just...
Well, what do you mean by how the AI should do?
AI, what we are doing is confusing fluency with understanding, confusing traditions with understanding of the world, trying to recreate the physical laws by total prediction, and it's the same as we would say that our brains work
I think like
it's not the same.
No, it's different. It's different.
Putting constraints, putting limits, why we don't do that? We are just generating this huge slope and just then complaining that it's too expensive to maintain this slope.
Yeah, so I think like AI tends to be expensive. I think if it can be cheaper, I think that would be revolutionary. That would be good. That would be good.
I mean, can be much better.
Yeah, okay. Then that poses a problem. Like there's a much less job opportunity for the humans because they are going to be cheaper.
Thank you. Congratulations, Mr. Kitano, for your talk. Okay, here we are at a university, so we are talking about discovery, scientific discovery. which kind of new competencies and skills should we, as university, take care of?
Yes.
How to prepare people for this?
Okay, so I think like the really key, which I'm talking all the time, is epistemic diversity. We need to be able to identify the problem that need to be solved and for whom. And that's for probably like, for rare cases or long tail part, but like accumulation long tail part is a significant part of society. For example, like, one of the questions is like, for example, if you have like elevators, like 5 elevators and 6 elevators in the hall, and if you come up with like, the blind person, and the blind person can call the elevator, but won't be able to tell which box is open. Now, why? It's like it's designed by the people who can see things. It's like we don't recognize their problem like that because like there's no building which can identify, able to tell which box is open for the blind person. There are many problems like that. Like we don't really recognize their problem. Like if we can reduce the problem solutions much cheaper, then that can be economically viable. I think that the really key is like AI is driven by all the data. So like those are the data is scarce for those issues. That's the way AI is not good at that, basically. I hope, But like, that's probably like all the realities, all the stats says. It's like if you can, I think that the real value is to be able to identify the problem that need to be solved for the even for the rare cases, but makes sense, make people happy and better. I think that's like epistemic diversity is really the key for us. Actually, that's I think that's really the key.
Thank you, Mr. Kitano, for your talk. Thank you very much. A question on the impact of the adoption of artificial intelligence in scientific activity. Do you think that is there any risk that we are moving towards a two-speed scientific system divided between those universities, research institutions, and so on that have access to these artificial intelligence tools, models, even autonomous labs, and those that don't have access to these tools, or they cannot afford this new AI scientific?
I think like a biggest problem will be the once we got like a highly competent AI scientist, like the research institution with access to such agent, such as AI system, and then one who don't, has a big competitive difference. So that's why like everyone's pouring money into this right now. It's like Google, OpenAI, U.S. government, Anthropic, everyone's spending billions of dollars in AI science because they can monopolize scientific discovery, and that means a lot actually. And then that will accelerate, right? So that would be exponential difference if they got like if they are the first to actually make like a high competent AI scientist, they can discover faster. And that will accelerate the discovery even more. So it will be exponential difference. So that's why people are pouring money. So at the same time, I think if there always international collaborations, open source, and then also probably if you want a massive money into this, you want to be able to go something economically viable. But there are other things, just like a long tail. The other things which all the decision maker think is less important, turn out to extremely important. There's an interesting part, it's always the long tail part where the opportunity lies. So we can go for the long tail part, we find something extremely important which investment haven't done. So I think we can be completely contrarians, and that's like a university is allowed for. You will have a freedom to go after those people think it's a minor thing, turn out to be extremely important. It's like Jennifer Doudna's CRISPR-Cas9. That was virus infection defense mechanism for the archaea. Whoever thought that kind of archaea virus infection can be completely rewrite their genome editing technology, actually. This is really purely academic thing, right? And turn out to be a complete game changer. There are many things like that. So I think that's a fun part to be in academia, to be able to have the freedom to go after something very important, something people haven't looked at it, but turn out to be extremely important. That's really interesting thing.
Okay, thank you very much.
Thank you.